Have you ever found yourself puzzled by the complexities of algorithms? You're not alone. Today, we're diving into a fascinating question. How can an ON algorithm also be considered an ON squared algorithm? Let's unravel this mystery together. I totally get it. Big O notation can be confusing, especially when you hear that an algorithm can fit into multiple categories. It's like trying to fit a square peg into a round hole. Frustrating, right? But don't worry, we're here to clarify this for you. So let's set the stage. One user recently asked, how can an ON algorithm also be an ON squared algorithm? They were confused about the implications of Big O notation and wanted some examples. Sound familiar? Let's break it down. To understand this, we need to remember that Big O notation describes the upper bound of an algorithm's complexity. An ON algorithm can also be ON squared because ON squared is a broader category that includes ON. It's like saying all squares are rectangles, but not all rectangles are squares. And stick around. At the end of this video, I'll share a simple example that will make this concept crystal clear. You won't want to miss it. To understand how an ON algorithm can also be classified as ON squared, we first need to clarify what Big O notation represents. Big O notation describes the upper bound of an algorithm's time complexity, meaning it provides a worst-case scenario for how the algorithm performs as the input size grows. Now let's consider an ON algorithm. This type of algorithm processes each element in a list exactly once. However, if we were to add another operation that involves iterating through the same list for each element, the complexity could change. For instance, imagine an algorithm that finds the maximum value in a list of numbers. This is an ON operation. If we then add a nested loop that compares each element to every other element, the complexity becomes ON squared. It's important to note that while an ON algorithm can be considered ON squared in terms of upper bounds, it doesn't mean it will always perform at that level. The actual performance will depend on the specific operations being performed. In summary, any algorithm that is ON can also be classified as ON squared because Big O notation focuses on the worst-case scenario. This means that while the algorithm may perform efficiently in practice, it is still important to recognize its potential upper limits. Fun fact, the term Big O was introduced by mathematician Paul Bachmann in the late 19th century. Who knew math could be so historical? Now, let's look at the answers provided by other users. According to this user, it's correct to say that an ON algorithm is also an ON square algorithm. They explain that ON algorithms are a subset of ON square algorithms, similar to how squares are a subset of rectangles. While it's technically accurate, it's not the most precise way to describe it. That's all on that answer. Let's take a look at another one. According to this user, an ON algorithm is also considered ON squared because it grows slower than both n and n squared as n becomes large. Essentially, if an algorithm is ON, it will also fit within the bounds of ON raised to any power greater than 1, like ON squared. This means that for large inputs, the performance of an ON algorithm is still less than that of ON squared. That's the end of that answer. Let's see another perspective. The user explains that in Big O notation, a function f(x) is considered O(g(x) if it is bounded above by a constant multiple of g of x for sufficiently large x. This means that if g1x is less than or equal to g2x, then f(x) can also be considered Og2x. Therefore, an ON algorithm can also be classified as ON squared because n is less than or equal to n squared for large values of n. Now, let's shift our focus to a different response. This user explains that an algorithm with a single loop has a time complexity of ON, while one with a nested loop has a complexity of ON squared. They use the bubble sort algorithm as an example. When given a sorted input, the inner loop doesn't execute, making its complexity ON. However, in other cases, it remains ON squared. Here's the takeaway. When analyzing algorithms, remember that ON is a specific case of ON squared. Understanding this can help you better evaluate the efficiency of your code. And there you have it. You now understand how an ON algorithm can also be classified as ON squared. If you found this explanation helpful, please hit that subscribe button for more insights into the world of algorithms. Keep exploring, and happy coding!